Hello guys, this video is continuation of our last lesson about the bit logic operations. Until now, we have learned all bit logic operations. In this video, after a short introduction, we are going to see how a PLC program can be tested with the force table, SIM table, and also the Factory IO software. We can simulate some industrial processes using the Factory IO software and then connect it to a PLC to control the process. Finally, we are going to do a simple project with the Factory IO to teach you how to use it to simulate your industrial processes. Before we get started with today's video, I just want to inform you about all the great content I have been releasing on the plcgoods YouTube channel, which includes topics related to industrial automation, PLC programming, HMI and microcontroller based developments and projects. My name is Saeed Reza Fattahzadeh, and if you enjoy this video, I would appreciate it if you could click the subscribe button as well as the notification bell to receive the latest and greatest content I will be posting through the channel. Please be informed that by clicking on the join button and paying a small monthly fee for as long as you want to continue, you can become a channel member to get access to cool perks such as to have access to my exclusive videos, WhatsApp support number, and access to PLC control program codes existing in my YouTube channel. I will add more or edit these in the future and do my best to not to disappoint you and create these hard-hitting tutorials and content that you all like, but I am still growing and I am expanding the channel as well. At the end of the day, I still appreciate your support and consideration. Alright, do you remember this PLC wiring and this program? Now let's see how a CPU executes a program. When the CPU is in the run mode, it stores the state of all its inputs on the image input memory, and then it runs its program from the first line to the last one. See here, when the CPU needs to use the state of an input such as I0.1, it reads this input state from the image input memory, not from the physical PLC input. Also, when the program changes an output state, such as Q0.0, a PLC does not change its physical outputs until it executes the last line. After the CPU executes the last line, it updates all outputs. After that, again it stores the state of all inputs and runs the program. And this cycle is continued as long as a CPU is in a run mode. This cycle is called the program cycle or scan cycle. It lasts about 5 milliseconds. You can transfer your program to your PLC and test it if you have a PLC connected to your computer. Otherwise, you can use a virtual PLC to test the programs. Now let's test this program. First, let's save it, then compile it to see if there is any error or warning in our project. Then if you have a PLC which is connected to your computer with a LAN cable, click on this icon to make the TIA to search your PLC. Otherwise, click on this icon to start the simulation. Some CPU models don't support simulation, so you will need to change your CPU in device configuration. Fortunately, my CPU supports it. When I click on this icon, I can see the program which is uploaded into my connected PLC, either the real PLC or the virtual one. If there is a difference between the TIA and the PLC program, this icon does not work. Now, with these green or blue lines, we can understand the state of the virtual power, which shows the result of logic operations, RLO. Also, we can see which inputs or outputs are activated. Now let me change the state of I0.0 address with the force table. Well, usually the force table is used in maintenance processes. For example, when a push button is not working. Now let's see what happens here. See this slide again. We use the force table to change the state of inputs on the image input memory, not at the PLC inputs. So the state of a PLC inputs may be different from their values on the image input memory. Therefore, TIA shows these red F letters to make a programmer to notice this point. Also, like this green line, we know how a watch table can be used to see the state of an input or output addresses. Alright, now we are going to see how we can use a SIM table to change our virtual PLC inputs. Here on the virtual CPU, click on this icon. Now create a new project. Now create a new SIM table or use this one. Define the inputs which you want to change. Let me have a better view. Well, like the force table, you can change the input addresses with the SIM table, but as you see here, there isn't any red F letter. Do you know why? See this slide again. When you have a real PLC with this wiring, you can change the PLC inputs using S1 or S2 switches. With the SIM table, we can change the state of our virtual PLC inputs as we can with a real PLC. In this way, we cannot change the image input memory directly. Thus, the TIA does not show any red F letter. Another point about the virtual PLC is these icons. Although S7-1200 CPUs don't have these icons, other CPUs might have them. When the PLC processor is in run, stop, or pause mode, the CPU is actually performing those tasks respectively. The last icon, MRES, is used to clear a CPU memory or to reset it. Now let's simulate this program in a different way. Let me launch the Factory IO software. Its free trial version can be downloaded and used for 30 days. After that, you need to purchase and install its license. Now let me show you what this software is good for. With the Factory IO, we can simulate industrial processes in our computer. It usually includes some electrical equipment such as push-button sensors, lamps, or motors. When our computer is connected to a PLC like the S7-1200 model by a LAN cable, the Factory IO can send its sensor or push-button states to a PLC and receive any suitable state for its actuators from a PLC. In other words, you can test your PLC programs in a simulated industrial process environment without using any electrical component or wiring. Also, this software can be used with the TIA simulator, S7-PLCSIM. Let's learn this software from the first step. This software has a graphical help. For example, here you can see the settings in which you need to connect the Factory IO to S7-1200 or S7-1500. Or here you can find settings in which you need to use for the PLCSIM beside the Factory IO. Pay attention, you need a template when you want to use the PLCSIM. Here are some suitable templates for S7 PLCSIM version 13 and version 14. Also, you can find a suitable template for S7 PLCSIM version 15 or version 16 on the internet. Well, to see how we can connect the Factory IO to the PLCSIM, first let's create a simple industrial process. Let's click here to create a new plant. I can use my mouse to change my camera angle. Let's select a belt conveyor and insert it into the plant. See here, this belt conveyor has a motor. Its name is belt conveyor number 1. To set a height to a component like this box, I first press the V key on the keyboard and then use the mouse to change its height. Now let's insert a green and a red push button to start and stop the belt conveyor motor. Now we want to connect the programmed PLC to the Factory IO to control the electrical parts of the design plan. Remember that we need to use a suitable template based on our PLCSIM version. This is my template that I can launch from the TIA. So let's launch the TIA and this template. As you can see, the main difference between this template and our previous program is this block inside the first network. To use the PLCSIM beside the Factory IO, we must not change this block. So let's write the program in the next network. Now I compile and start the PLCSIM. Okay, now I have a virtual PLC linked to the program. I want this PLC to control the plant which I designed in the Factory IO. In the Factory IO, when I click on this icon, I see the actuators tag, such as this belt conveyor motor. Let's change my position with the arrow key. When I click on this icon, I see sensor tags such as push buttons that can be connected to a PLC inputs. As you can see, I can select or change name of any sensor or actuator. When I select a component like this stop push button, it has three states which are no failure, injecting an on failure, and injecting an off failure. For normal conditions, select the no failure state. As you see here, with this icon, each component can be activated manually. Alright, we want the virtual PLC to control this plant. So open the File menu and select the drivers. Here select your CPU type. I use the PLCSIM. From the left list, I determine which component in the design plant must be linked to my virtual PLC. From the right list, I select which actuator should be controlled by my PLC outputs. Now click on the Connect. This icon means my PLC is connected to the Factory IO and the design plant successfully. Let's start the simulation. Alright, here is the problem. Let's check the PLC program. As you can see, the stop contact does not pass the virtual power because it's activated by this normally closed push button. But my program is written based on the normally open push buttons. Let me modify this program and transfer it to the virtual PLC. Now let's test the designed plant. As you can see, I can turn on or off the belt conveyor motor with these push buttons. Also, I can see the program logic. Up until now, we have seen various ways to simulate our PLC programs by using the force table, sim table, and Factory IO. Now, I am going to link the Factory IO to my PLC and test a simple program. Let's get into it. I have an S7-1200 CPU. It can be linked to the Factory IO. The Factory IO has a graphical help to show how it can be linked to PLCs. Let's see the necessary settings for S7-1200 CPUs. Its requirements are Siemens Edition or Ultimate Edition, S7-1200 or 1500 PLCs, and the TO portal. Then we can see the steps for setting up communication between the computer and the PLC. So let me create a new project in the TO portal. The next step is configuring my PLC in the TO. Like the previous videos, I select Configure a device and click on Add new device. As you know, here I can find and insert my CPU manually based on its article number. But there is an easier way. Let's select this item, unspecified CPU 1200. Later, the TO will detect the PLC automatically. This message says to specify the CPU manually or detect the connected PLC automatically. Now select the connection type and click on Search. The TO portal has detected my PLC. I can click here to flash its LEDs. Now let's click on the Detect. Notice that the TO portal has detected my CPU and the analog module which is installed beside it. Pay attention, after these steps, if you are adding a PLC that is not in the same subnet as your computer, you will be prompted about assigning a new IP address to the network interface. If this window appears, click on Yes. Well, in the next steps, some properties of the inserted PLC need to be modified to allow the communication with the Factory IO. First, we need to define the IP address of the connected CPU. So let's go to its Properties panel. My CPU address is 192.168.1.23, which can be changed. The main point is all devices that are in the same network must have a different IP address. Now pay attention to step 10, which says PLC physical inputs by default use the first memory addresses of an input image memory. For the Factory IO to be able to write sensors values to input image memory, you must offset the input addresses. We recommend an offset of 10. Let's do this step in the TO. When I change this number, the physical input address starts from 10 instead of 0. With this setting, I use I0.0 to I0.9 in the Factory IO and consider the next addresses for the physical inputs. Because an address on the input image memory cannot accept two values from two sources such as the physical inputs and the factory I/O. Otherwise, the values written by the factory I/O is overwritten as the state of physical inputs is copied to the input image memory. Finally, we must give full access to the PLC memory. Let me do these settings in the TIA. Alright, this setting is for the PLCs with the firmware of lower than version 4.0. Now our settings must be transferred to the CPU. Let's do that similar to the previous videos. Alright, settings have been transferred to my CPU. Also, we need to do some setups in the factory I/O. Let me show it. First, I select drivers under the File menu. Then I select Siemens 12-1500. Then click here to make sure a right PLC has been selected. Also, the IP address of the selected PLC must be inserted correctly. Now the factory I/O can be linked to the PLC. Now let me write a simple program in the TIA. I want to use an SR instruction to turn output on or off. I want to use the first switch to turn on a motor that is connected to the physical input of my PLC, so I can select and drop its address in my program. Similarly, I can use other physical inputs, but let me show you how virtual inputs can be used from the factory I/O. To stop the motor, I can use the next physical input. Instead of that, I want to use the stop push button which has been inserted in the factory I/O. So here I can connect the inserted stop push button to this PLC address. Pay attention that these addresses are different from the physical PLC input addresses. So to stop the motor, I use the address that is defined in the factory I/O. Alright, let me define suitable tags for input addresses and complete this program. Well, this program can turn on or off the Q0.0 output, which is the first physical output. Also, I can use this output to turn on my belt conveyor, which is already inserted in the Factory IO. Now let's upload this program to the PLC. To upload the program, the CPU needs to be in its stopped mode. The program has been transferred. Now I can start the CPU. If I select the no action mode, the CPU remains off. I can start or stop the CPU from here. Now let's start the CPU and activate the program monitoring. Alright, let me have a better view of my program in the Factory IO and the PLC. Let's change this contact to a normally closed one, because the stop push button in the Factory IO is a normally closed one as well. Now I have to download the modified program to the PLC. Let me test the program. As you can see, based on my program, I can turn on the first output with the first physical switch. If I open the first switch, the output remains on. To stop the PLC output or the belt conveyor, which is connected to the output, I should click on the stop push button in the Factory IO. In this video, you'll learn how to link the Factory IO to a S7-1200 CPU. You can take the same steps to link the S7-1500 CPUs to the Factory IO as well. Also, you learn how you can use physical inputs or connect virtual equipment in the Factory IO to your S7-1200 CPU. In the next videos, I prefer to use the Factory IO to simulate the programs instead of using the physical switches. Now we are going to use some bit of logic operations in an industrial process. We want to write a program to sort boxes based on their height. We are going to use the Factory IO and the PLCSIM software to simulate the project. In this plant, we have a conveyor, a control box, and a pusher to push the boxes. From here, some boxes enter the plant and the conveyor moves them. Each box is either a small or a large one. Here is a sensor that detects large boxes. So a small box will just go on this conveyor, but the larger ones will be pushed by this pusher on this chute conveyor. Let's get into it. First, let's start with this plant to design the new plant. Insert an emitter. To change the height of any device, press the V key on the keyboard and then change its height with the mouse pointer. Now right-click on the inserted emitter and unmark these. Just keep the small and large boxes. Now let me move this control box. Now insert a pusher. With this pusher, we can push boxes. Also, this pusher has two sensors. If the pusher is not extracted, its back limit sensor is on. So this sensor, its front limit sensor, determines whether the pusher is extracted 100% or not. Now let's insert a diffuse sensor. When a box with enough height appears in front of this sensor, it will send a signal to the PLC. So with this sensor installed virtually, we can detect the large boxes. Now I need to insert two chute conveyors. Now let's insert two removers at the end of each chute. Also, from the operator list, insert an emergency push button and two green and red indicators. Finally, insert a warning lamp. Now we need to write the PLC program. Let's start with this program from the previous video. Now we have some sensors and actuators that must be linked to the PLC inputs or outputs. First, let me define suitable tags based on the name of these devices that are used in the design planned by the Factory IO. From the previous exercise, here are the suitable tags for the first PLC output and the I0.0 and I0.1 addresses. We have an emergency push button with the I0.2 address as the PLC input. The next tag is the diffuse sensor, which is connected to the I0.3 of the PLC input. The next PLC inputs are linked to the pusher front and back limit sensor. Pay attention. When I'm defining tags, each tag in the address column automatically gets an address that is exactly after its previous address. Since the Q0.0 is already used for the belt conveyor, I will connect the pusher to the next PLC output, which is the Q0.1. I go ahead and link the other actuators to the next PLC outputs. Now let's start programming the project. This program uses the start and stop push buttons to start or stop the belt conveyor motor. In the next network, I use an SR instruction to turn the pusher on or off. I want to push large boxes when they have passed completely from the diffuse sensor. So, in the program, I need to scan for the negative signal edges received from the diffuse sensor. When the pusher front limit sensor generates a signal, it means the pusher has pushed a large box completely, and it must be reset to return to its normal condition. In the next network, I want to write a program to turn on the warning lamp and the green indicator when the belt conveyor motor is on. I want to turn on the red indicator when the belt conveyor motor is off as well. So the red indicator works inversely compared to the belt conveyor. So let's use a negate assignment in this network. Alright, the program is complete. Let me use the positive edge of the front pusher limit to reset the pusher. Remember, I need to have this block to use Factory IO. Now let me launch my virtual PLC. Now let's launch Factory IO and under the File menu, click on Driver. Now click here to connect Factory IO to the virtual PLC. Now, based on the use tags and their input-output addresses, select and link the devices on Factory IO to the PLC IOs. Now let's control the design planned with the PLC. As you can see, with these green or blue lines, you can see what is happening on the PLC beside the Factory IO. I hope you have learned the bit logic operations. Now you can simulate some industrial processes with the bit logic operations and the PLCSIM. Also, you have learned how to use Factory IO. Now, we are going to see how we can transfer and test the project with our PLC, which has been done with the TO simulator. Alright. We have seen how we can use a template of the TO portal to connect both the virtual PLC and the Factory IO. Now let me do the sorting box project with my real PLC. First, I click on Add New Device. I am going to configure my PLC in TO. Instead of finding my devices manually, I select Unspecified CPU 1200. Now I click on Detect. TO will try to detect my connected hardware. Like the previous videos, if I click here, PLC LEDs should start flashing, but it didn't happen. Remember I told you when we are going to connect real PLCs, we need to close all virtual PLCs. So let me close the virtual PLC and try again. At this time, the TO has detected my hardware and PLC LEDs start flashing. Alright, my hardware is detected and configured in the TO portal. I need to use this PLC address in the Factory IO. Also, let the PLC inputs address start from 10 instead of 0, like in the previous videos. My CPU supports 2 analog inputs, so I must remember not to use them in the Factory IO. Also, let me change my CPU protection setting. I already explained these settings in the previous videos. As you can see, the inserted PLC doesn't have any program. I can use the sorting box program which has been written in the main block. So let me copy the previous main block and paste it here into the program blocks folder of the new programming project. Now I click on OK to transfer my sorting box program. Pay attention. This open main block belongs to the previous PLC project. So let me close it and open the transferred main block, which is located in the second PLC project. Remember, we needed this function to connect the virtual PLC to the factory IO, which was defined here in the previous PLC project. Now I am going to use my real PLC, so I don't need it and I can delete it. Also, we have defined some tags in the sorting box program. The new PLC project needs to know each tag address, so I need to transfer the PLC tags table as well. Now, TIA portal knows each tag belongs to which address based on this tag table. Alright, the sorting box program is transferred to the new PLC, and now I can transfer the PLC program and its hardware settings. Pay attention. None of these input addresses in this program matches with physical input addresses because I want to change them from the factory IO, not from the physical inputs which are connected to the PLC. In the factory IO, I need to check some settings. First, I must select Siemens S7-1200. Then I go to configuration and match this IP address with the IP address of my PLC. Also, check the S7-1200 is selected. Now, the factory IO can connect to my PLC. Then I link the factory equipment to my PLC. Now let's test the program. As you can see, my physical inputs don't work because I don't use them in my program. But I can start the factory process with push buttons, which are inserted in the factory IO. Also, you can see which output is on by viewing the PLC LEDs. For example, the second output of the PLC is connected to the pusher in the factory IO. Alright, if I want to use physical inputs, what should I do? That's simple. I just need to use physical input addresses. Let me change the start and stop push buttons addresses to the two last physical input addresses, which are I10.6 and I10.7. Let's transfer this program. Let me activate the program monitoring. As you can see, in this case, physical inputs have been used in my program, and I can start the factory process with my last physical switches. Now these start stop push buttons don't work. If I want to stop the process based on my modified program, I must use the switch. When the factory process is stopped, just this signal lamp is on, which is connected to the third PLC output. Alright, you can try to do this project with the virtual or your real PLC, and also use the real equipment like my switches or virtual equipment such as the pusher in the factory IO. In the next videos, I will prefer to use only the factory IO equipment and do projects using the TO simulator, so you won't need any hardware in this tutorial. Conclusion. Until now, we have learned bit logic operations and how to use the factory IO linked to the TO simulator or a PLC to test our programs. In the next video, we will start to learn about S7-1200 timers. Thank you for watching this video.